So actually, this is a little bit a continuation from what Matt Reuter does, actually. I'm in the departments of physics and astronomy, and we are also doing quantum mechanical simulations of materials. And actually, one of our favorite systems of study is liquid water. Here, what you're seeing is actually a simulation of liquid water. All these red atoms are oxygens, these are hydrogens. But actually, we are adding something extra to it, which is we are putting ions. And I mean, I could spend all day, all month, all year talking just about water. We've been basically simulating it for years and trying to understand it using quantum mechanics. And that actually means that it's not like I'm putting here my atoms and I'm fixing what are the charges on the atoms. I'm putting all the electrons on them and I'm letting the electrons free do whatever they want in my simulations while everything moves around. And what I'm interested on is what are the final structural and dynamical properties of these systems. And it comes out that despite this is such a simple system, liquid water, we are actually not, well, we are getting better, but we are not yet there to describe such a simple system using as much quantum mechanics as we can put in our underlying equations as we can, because actually there is a lot of complexity hidden in the system. And so what we are doing now is, well, we've understood very well what's going on just with liquid water. So can we now poke it if we put ions in the system and see how it is perturbed? So I'm talking about actually this project. There are many other projects going on in my group, but I like this project first because it's actually very new. It's a project that my student Alex Wills is working on. And I think it's a really neat introduction to understanding the differences between classical and quantum mechanics. So the title of the talk was Opposite Charges Do Not Always Attract. So what we are doing is putting sodium and chloride in liquid water. And this is basically what is the electrostatic energy or the total energy that caused of separating two ions, just here, just point ions, just forget about the size of them, and if they were in vacuum. And so basically the ions want to be in exact contact when they are in vacuum, and it actually costs a lot of energy to separate it. The ions want to touch each other. And so what happens if I put them in a medium, in a dielectric medium as water? And so the first thing I can do actually is just, we can approximate, is just put it in some sort of constant dielectric medium and see what happens, is what I had before. And the only thing that's it is that, yes, it's still, the ions want to be together, they want to touch each other, but there's a reduced energy cost. So the dielectric basically is screening these charges, and it now costs less energy to separate them. So what happens if I actually put them in real water? And so in real water, this is actually from the picture that you saw before, where that you have. Of course, here there will be like a vertical wall, so eventually the ions will touch each other and they will have a minimum distance related to the radius of these ions. But once I put them in actual physical liquid water, what you will see is that now you have regions where they still want to be together, and so this will correspond when the ions are very close together. But also there are regions where they actually repel each other. So as soon as you come to here, they repel each other and they want to be apart. And indeed, there is the question of, do they prefer to sit in this very close proximity, or do they prefer to sit farther away from each other? And there you are seeing two curves, because it comes out that actually understanding this is a very complicated problem. And the reason for that is that now entropy plays a really important role. So now what I have is not only the electrostatic energy of separating the ions, but I also need to account for all the possible conformations that water molecules can adopt around these ions and the corresponding energetics of these. And it comes out that actually doing this very accurately is difficult for two reasons. First is a computational reason, which is it is very expensive to do these simulations. And the second is an actual, in the sense that we need to do statistics, and statistics means repeating and repeating our simulations many times. But the second one is even calculating the interactions in these systems is expensive. So what you're seeing is that now when the ions are in water, the possible configurations that are sort of more stable as what we call the contact ion pair. So basically the ions are together but not completely together because water is also contributing to screen those interactions. Or slightly separated, so now water is surrounding the ions more and more, forming a cage around them, or fully separated. And the energetics of this is not only dependent exactly on the charges on each atom, because now the charges on the atoms can be very much delocalized, and we need to treat them quantum mechanically. And so we do that with our methods. I'm going to skip this. Great, thank you. And so our role basically is understanding how the quantum mechanical interactions can modify the entropy and the enthalpy of the system of this ion pair association. And what you're seeing here, these two plots that I'm showing, is basically the same type of simulations, changing a little bit the flavor of those quantum mechanical interactions. And the question is which ones are right, which of those two flavors is correct. And well, one way that we can go is look at what other methods, including classical simulations, do. And this set of spaghetti lines that you see here is how much things change as I change my interaction method, including classical methods. And the problem we have in here is that actually there is not an exact experimental number to compare against. So what we need to compare against is the most accurate quantum mechanical simulation that we can make. And so our role now is basically understanding what makes some methods. So this is a classical method, which is saying that the contact ion pair, when the ions are together, is the most stable, whereas many of the quantum mechanical methods say that actually separating the first coordination cell of water is the most stable method. So there is a question of which is the right one in here, and we are working on understanding that. And so just so as you get a glimpse of the kind of analysis we do to understand how we do this, is basically we get our simulations and we get the configurations. And one thing we can look at, I told you that there's entropy in the system, and the entropy basically what it measures is the number of configurations that the atoms can have, and we can somehow relate that to how much volume each atom has to move around. And so we can calculate something that is called Voronoi volumes and look at how these volumes change if we switch from classical mechanics to quantum mechanics. And what you'll see is that this is with quantum mechanical simulations. These are with classical simulations. And this, in here, what you're seeing is the average volume that each ion has as a function of separating the ions. So as I separate the ions, I look at what is the volume of them. And so what you see when we do just purely classical simulations, there's basically the volumes are very much correlated and they don't change much. So it's basically saying that there is not much charge redistribution in the system because the charge is fixed. So one of the things of the classical simulations is the charges are fixed. And so there's not much charge redistribution. Everything is correlated. Whereas when we do quantum mechanical simulations, we start seeing that there's much more structure. Actually, charges as I separate my ion, where the electron in the chlorine atom sits, will basically delocalize more. That will affect the water distribution. And so you see regions of correlation and regions of anti-correlation. And that, indeed, is even more stringent when we get to actually looking at the volume of the water molecules, where, again, in quantum mechanics, we see really large changes of how much volume can explore water molecules. In classical mechanics gives us very, very, very little volume change. So what this is saying is that, indeed, we do need to take into account these quantum mechanical simulations. Now the question is which is the best quantum mechanical flavor that we can put on it. So this is something that the students are working on. Basically, in the group, what we do is we run the simulations, but we also put the equations of these simulations, and we try to put more and more physical insight on those equations to get for those results. So this is a simple problem, and it comes out that it to be a complicated one. So it's a challenge for our ab initio simulations, but it's a good one because it is teaching us what extra do we need to put on them to make them more accurate. Okay, so this is it.
Questions from Marivi? Actually, I have one. If the energies in terms of being in contact or separated aren't known, is it at least experimentally known which is favored? I would have thought NMR or something like that would.
So the exact, actually, probably is Ken in Hill. He might know. So Ken D likely is an expert on this, and he has studied many of these using the classical simulations. But the actual energy of going from the first minimum to the second minimum is actually not known. So you know the full free energy. So the integrated work of fully separating them, but not the barrier between the two.
I have also a question. Around a charge, if you put a charge into an electron gas, you would, in your case it's water, you would get oscillations. They are known as Friedel oscillations.
Correct.
Is it something similar?
So in this case, the thing is that you are screening. You see the oscillations, I didn't show that. But in a way, you will see those oscillations on the structure of the water layers around that charge. So the waters are screening, but now you have to think that you're screening with dipoles. And so the Friedel oscillations are for basically sort of continuous charge, but when you screen with dipoles, you don't see exactly the same, but you see the formation of layers of different level of screening by those charges. Yeah.
Perfect. Thanks, Marivi.
Thank you.